All right, Calc 1 students, let's talk about Chapter 3, Section 5. In this section, we're going to look at implicit differentiation. This is our last section in the chapter. And implicit differentiation is going to allow us to take the derivative of some unusual, maybe not unusual equations, but equations that we don't usually... Sorry, the cat was attacking me. We'll take the derivative of some equations that look like they might otherwise not be possible using the derivative techniques that we've looked at so far, but I'm going to show you how we can use those processes and concepts. And one of these concepts in particular is going to be a little bit challenging, so let's get to it. Oh, I'm back. I'm gone. I'm back. And the cat might have to go. Can we get the cat to go? Oh, there we go. Bye-bye. The types of equations that I want to look at you. I'm already looking at you. That I want to look at with you are not ones like this. This we can handle. These we've seen before. But check this out. Look at equations 1 and 2 here. These are tricky. They might not look tricky at a glance, but they're a little bit tricky because they don't say y equals. The y variable is kind of tangled up in the rest of the equation. So normally what we're seeing on these slides is that an expression or an equation is defined explicitly in terms of another variable. So y equals, and then we only have one variable on the other side. It might occur multiple times, it might be raised to a power, but there's only one other variable. So that's why we're seeing this statement here that says y equals f of x. The whole right-hand side is a function of x. That's not the case in equations 1 and 2. Here, we say that the relationship between x and y is defined implicitly. So that's why we have this process called implicit differentiation. It allows us to take the derivative of an equation where the variables are defined or related implicitly. I don't know if you're a pet owner, but my cat has taken a fascination with... Oh, you can't see it. It's too blurry. How do I... It's a twisty tie. She's just elated. Do you want to come say a quick hello, and then I'll give you your twisty tie outside? Will you look up? If I put your twisty tie up here, will you look up and say hello? That's Sophie. Oh, see, she's obsessed. All right, she's easily entertained. Now she's going to be easily entertained outside. Go out there and play. All right, one cat's out, one cat's in. Let's see if we can get some work done. So we have some options for how we take a derivative of an equation like this. We could take the equation and solve it for y. Now the first equation that we saw on the previous slide, x squared plus y squared equals 25, is the equation for a circle. And if we take that equation and we solve it for y, we end up having to take the square root of both sides of the equation at one point, which means we end up with a plus or minus square root. So in solving it for y, we really end up with two different functions, one with a positive and one with a negative. And then if we want to take the derivative, oh, here's just an illustration of how the original equation appears, and then if we sort of chop it up into two separate actual functions. And before we talk more about that first equation, if we look at this second equation, which was x to the third plus y to the third equals 6xy, which is a very specific curve, the Folium of Descartes. If you don't know, Descartes designed the xy coordinate plane. It's called the Cartesian coordinate plane. Cartesian as in Descartes, Cartesian. Okay, so we're really operating in his realm right here. So he's sort of named this particular curve as the folium. If we wanted to take and break this curve up into separate functions so that we could take the derivative using our normal processes, we would have to break it up into 3 separate functions. Look at this one, it's got this little tail going off here. However, each one of these graphs is a function. It passes the vertical line test, but we don't want to have to go through the motions of taking every implicitly defined equation and breaking it up into 3 or more separate functions in order to take a derivative. So what I want you to start doing is thinking about these types of functions not as x to the third plus y to the third, the original functions off the screen, but instead of thinking of the y value, I'd like you to think of the y value as some other function of x. We could go so far as to solve for y, in which case y would equal a bunch of stuff involving the x variable. So there is a y value. We're just not going to figure out what it is. It's not so much a y value as a y equals some expression in terms of x. We're not going to determine what it is, but I want you to start thinking of y as being a function of x, because it is. We could make that happen. We could write that up in every case. We just don't want to do that because it's way too much work. So we use this method called implicit differentiation. And you're welcome to read through these slides, but let's go in and take a look at an example. So we're going back to the first equation, x squared plus y squared equals 25. We're going to find dy dx, the derivative of y with respect to x. Remember, that doesn't actually say d, it's a lowercase delta. It's the change in y over the change in x. It's the slope of the tangent line at a particular point. Eventually, it's the rate of change of our function at a particular point. So when we find dy dx, we're finding a new equation, a new function that's going to help us determine slope of a tangent line. In order to determine the slope of that tangent line, we're not even going to plug in only an x value. We're going to be plugging in an x and a y value. And that's going to help us find our slope, our m value, so that we can write the equation of the tangent line. So process number 1 utilizes implicit differentiation. We're going to take the derivative of both sides of the equation. So here we go, taking the derivative of both sides. Haven't actually done anything, just putting that d over dx there. And then we'll, on the left-hand side, we'll distribute the d over dx. So this is going to these two terms. We're allowed to do that. So here's the derivative of x squared, the derivative of y squared. Over here, we've already taken the derivative of our constant value, which has turned into a 0. But we haven't yet taken the derivative of these two terms on the left-hand side yet. Let's just focus at the second term, taking the derivative of y squared. Let's look at this with me. Taking the derivative of y squared with respect to x. Now remember, don't think of it as the letter y or the variable y. Think of it as f of x. It's some function. Y is some function of x, which means that y squared is some function of x squared. And if I took the derivative of this thing, I would have to use the chain rule. The chain rule says we would take the 2 and multiply it out front, and we would keep the inner function, f of x, and we would decrease the exponent by 1, so it becomes a 1, though we don't normally write that, and then we would have to use the chain rule and multiply by the derivative of the inner function. So we would have an f prime of x. See this 2 right here? See this 2 right here? See this f of x right here? That's this y value right here. See the f prime of x? That's the dy dx, the derivative of y with respect to x. Y prime, f prime. Okay? it's important that you start to realize that, or if you just go ahead and realize immediately, instead of starting to realize, that these three components match up. Y is a function of x, and we're going to treat it that way without knowing what f of x actually is. But it's this, if you have to watch this a handful of times, whatever it takes, in order to perform implicit differentiation reliably, you're going to need to get into your mind the idea that the y variable is actually a function of x, and we have to use the chain rule, not even knowing what that function of x is. We'll see some more examples. So these elements are coming down to here. Right over there, where it says d over dx of x squared, right? This term is coming down here. The derivative of x squared is 2x, and the derivative of that constant value was 0. That used to be a 25. So we have all of our components now. We've taken the derivative. We've used implicit differentiation. And our goal was to solve for dy dx. We wanted the rate of change of y with respect to x. We want slope. We want rise over run, change in y over change in x. That's dy over dx. So if we take this equation and we solve it for dy over dx, subtract 2x from both sides, and then divide both sides by 2y, we will end up with dy over dx equaling negative x over y. Now, in order to find the slope of the tangent line at the point 3, 4, this is different than what we've done before. We're not just going to plug in the x value. We have to plug in the x and the y value in order to determine the slope. The 3 goes into the numerator, the 4 goes into the denominator, and we've done it. We found the slope of the tangent line, negative 3/4. We take that, we incorporate it into point slope form. Here's y minus y1 equals m times x minus x1. Plug the 3 and the 4 and the negative 3/4 in there. Clean it up a little bit, distribute, maybe move some things around, and we have the slope of our tangent line. This is maybe an unusual format to write the equation of the tangent line. We would typically write it as a y equals mx plus b equation, but you could convert this equation over to look like point slope form, or sorry, slope intercept form, y equals mx plus b form, if you wanted to. Solution 2 is redoing the problem that we just did, except instead of doing implicit differentiation, we've solved for y equals. We know that the point 3, 4 is on the top half of the circle, so we're using the positive version of that y equals equation. We come down to the next slide, we actually take the derivative of that equation. The derivative of that equation looks like this. That doesn't look nicer than our very condensed derivative that we've came up with using implicit differentiation. This looks way more complicated than negative x over y. However, please realize you see what I've circled right here? Y equals the square root of 25 minus x squared. This was our derivative up at the top of the screen. Negative x over y. If we replace that y value with the square root of 25 minus x squared, then we would have that the derivative dy over dx equals negative x over the square root of 25 minus x squared. Look familiar? So either way, you can get to this same destination. I think that it is a far more versatile tool to master implicit differentiation, especially as the equations get more complex. You're not going to want to try to solve for y before taking your derivative. But an illustration that in that case it is possible to get the same solution. Derivatives of inverse trig functions, I'm not going to talk to you about the backstory. I'm not going to derive any of these derivatives for you. I'm simply going to, well, I could pause on a couple of these slides for you if you wish. What I want to do is get down to our last slide of the section and our last slide of the chapter. So here's a couple of example problems. We'll do a couple of example problems. I'm going to toggle over and look at some homework problems after this. But you can have these for additional reference if you'd like to try to work these out and then compare your answers and solution processes to these. I welcome you to do that. And here is a table of the derivatives of your inverse trig functions. You should have this in your notes. So I'm going to pause for a moment and switch over to the to look at some homework assignments with you. See you in a second. All right, so here we are looking at a couple of additional example problems. Let's work some of these out. Our first task is to find dy dx by implicit differentiation given this equation. You could solve this for y, but I'm not real excited about taking the cube root of both sides, although you could do that. It would not be impossible. But look down at number 2. I don't want to work on problem number 2 and try to solve that thing for y. So let's get into the groove of using implicit differentiation. When we take the derivative of both sides of this equation, I suppose we could write it all out. D over dx of x to the 8 plus y to the 3 equals, and we'll take the derivative of the right-hand side. On the left-hand side, we'll distribute the derivative process. So we'll take the derivative d over dx of x to the 8 plus we'll also take the derivative with respect to x of y to the third. Think of it as f of x to the third. In fact, let's try it. Let's just go ahead and write f of x in brackets to the third. F of x to the third. It's a little bit of a hack, but let's try it. So we're taking the derivative of that whole thing, and the derivative of a constant value on the right-hand side of our equation is equal to 0. Great. Now let's go back from left to right again. The derivative of x to the 8. That is a derivative that we're sort of used to, that we've done before. So the 8 multiplies out front, the variable stays there, and the exponent gets decreased by 1. Plus, now we have to take the derivative of f of x to the third. So it's some unknown expression being raised to the third power. We have to multiply the exponent out front, and then we keep the function, the inner function. We decrease the exponent by 1, and then we have to multiply by the derivative of the function, f prime of x, still equals 0. So this, going from here to here, we did that because we needed to use the chain rule. Have to multiply by the derivative of that inner function. Now over here, you should put some kind of a little note that we're going to, let's see, we should go back and put in one more little note also. Maybe we could say, let y equal f of x. There we go. That way we know that we've replaced our y values with f of x. And then we could change back. Let me erase this squiggle. Let's replace f of x with y. So we have 8 times x to the 7 plus 3y squared times dy dx equals 0. F of x is a function of x. Y is a function of x. So f prime of x and dy dx are equivalent. All right, we're just swapping notation a little bit here in order to be working with something that looks a little bit more familiar to you. That idea of using the chain rule when you have a function or an expression being raised to a power. All right, from here, it is just arithmetic. We need to solve for dy dx. I'm going to subtract 8x to the 7 from both sides. And then I will divide both sides by 3y squared. And we've done it. Ladies and gentlemen, we have performed implicit differentiation. Again, I think the biggest challenge for you is getting used to the fact that y is a function of x and therefore requires that we use the chain rule. But that's it. That's the biggest challenge in implicit differentiation, is remembering to use the chain rule. So let's do this one. Well, should we do this one? I feel like we should do one that's even more difficult. I'm going to leave you to do number 2. And just remember that you need to use the product rule in here. And you'll be using implicit differentiation because you're going to be taking the derivative of y as part of using the product rule in that middle term. You'll of course be using the chain rule in here also because you're taking the derivative of y, or think of it as f of x. Let's go down and look at number 3 in greater detail since this is a little more unusual. We have 6 times a couple of trig functions. So let's take the derivative of both sides, and in fact I'm going to factor the 6 out of that derivative process right away. Let's see, let's write this as 6 times the derivative d over dx of cosine x cosine y equals the derivative d over dx of 5. And on the left-hand side of our equation, we have a product of these 2 trig functions, so we're going to use the product rule there. So this is equal to 6 times. I'm going to keep my first factor, cosine of x, and then I'm going to multiply by the derivative of the cosine of y. The derivative of cosine is negative sine, so I'm multiplying by negative sine y, and then I have to multiply by the derivative of y with respect to x. And there it is, dy dx. Plus, I'll take the derivative of the first factor, the cosine of x, which is negative sine x, times that second factor, cosine y. And that does it for the product rule. On the right-hand side becomes 0 because the derivative of a constant is 0. So again, cosine stayed the same. The derivative then of cosine y became negative sine y, but the chain rule says we have to multiply by the derivative of the inner function. And the inner function in that case is y. What's the derivative of y? I don't know, because I don't know what y is. So we're just going to write down, once somebody tells us what y is, we'll take the derivative of it. And here it is. The derivative of y with respect to x. I don't know what that is, So I'm just going to leave it there. And then over here is the other half of the product rule. Nice. Okay, so let's clean this up and eventually solve for dy over dx. So it's just algebra from here. That multiple of 6 on the left-hand side, I'm going to let that go. I'm going to divide both sides of my equation by 6. The 6 on the left cancels. That 0 that's on the right-hand side divided by 6 is going to stay a 0. And I can't handle the cat meowing outside the door anymore. I don't know if you can hear her. She's cute, but she can be really annoying. Come in here. Come here. You were annoying before, and you're annoying now. I love you anyway. All right, so let's do a little bit of algebra. I'm going to add this term over to the right-hand side. It's a negative term. We're adding a negative value here. So I'm going to add it over to the right-hand side. Cosine of x. Now it's times negative sine y. So I'm going to put the negative to the left of it. And we'll keep the sine of y. And we'll keep that multiple of dy dx. Equals, we're adding that second term over to the right-hand side, which is sine x cosine y. We divided both sides by 6, so you should put a little note somewhere in your notes that says that you divided both sides by 6 and that 6 didn't just magically disappear. And now we can divide both sides by negative cosine x sine y. And it was negative, so I did put a little negative sign right in front of my division symbol there, my fraction bar. And then I think we could clean this up a little bit further. Sine x divided by cosine x is tan x. And cosine y over sine y is cotan y. So I'm going to say that this is dy dx. It's a lot. Okay, there's a lot going on there. But just keep taking it one step at a time, one line at a time. It's not even a lot by volume. It's a lot conceptually. There's a lot sort of tangled up in there. What else do we have that we could look at? On the left-hand side of the equation, you've got a product, e to the y times cosine x. So you'll have to use the product rule there. As part of the product rule in this problem, you'll have to take the derivative of e to the y. The derivative of e to the y is e to the y times the derivative of the exponent, which will be dy dx. On the right-hand side of the equation, you'll have to take the derivative of the sine function. The derivative of sine is cosine, so you'll have a cosine xy, and then you'll have to multiply by the derivative of the inside function. Let's just do this part. Let's just find the derivative of the sine of xy. I'm going to leave you to wrestle with this part over on the left, but I'm going to help you out with this part on the right. So the derivative of sine is cosine. We keep the inner function, and then we have to multiply by the derivative of the inner function. Okay, so what's the derivative of that? It is the first factor, x, times the derivative of the second factor, which is the derivative of y, which is dy dx, plus the derivative of the first factor, the derivative of x, is 1 times the second factor, which is y. It's a little anticlimactic. You'd wish that like some confetti came down or something to help you celebrate the fact that you just figured that out, but we just have to enjoy the satisfaction of knowing that we're going to get that answer right once we adjust this thing. You're going to have to distribute this multiplication by cosine xy to this term and to this term. And then eventually you're going to have to get all your dy dx stuff, all those dy dx factors, over to the left-hand side of the equation. So your work is not done here by any means. Get all of your dy dx terms over to one side of the equation. Factor dy dx out of those terms, and then divide the leftovers back over to the other side of the equation, away from the dy dx. That is how you're going to isolate the dy dx. Number 5, you're still taking a derivative using implicit differentiation. You just have to go one step further and find the equation for the tangent line. You can handle that part. Here you're finding a second derivative. I don't know if we've ever found a second derivative together. Let's do this one. So I've got 5 times 2x. So I took the derivative of the first term, plus 2 y times dy dx. So I've done my implicit differentiation there, equals 0. Right, because this 2 multiplies out front, so it makes it 2y, then we decrease the exponent by 1, so now it's 2y to the first power, 2y to the first power, but then we have to multiply by the inner function. Remember, y is the same thing as some other function of x, so we have to use the chain rule, multiply by the derivative of y. We denote that as dy dx. So this is this is a good start. Now let's isolate dy dx. So 5 times 2 times x was 10x. I've subtracted that from both sides, making it a negative 10x on the right-hand side. Now let's divide both sides by 2y. And then we can simplify that expression a little bit. Reducing by a factor of 2. So that is what you used to think of as f prime, or the first derivative of your function. Now it's dy dx once. Now we want to find dy dx again, so that'll be our second derivative. What kind of notation did we use over here? Y double prime. Okay. So when I take the derivative of the left-hand side of my equation, that is effectively going to be y double prime. And let's just switch over to that notation. Y double prime equals, and now we have to take the derivative of the right-hand side again. And that is, let me factor the negative 5 out, and then we'll take the derivative of x over y. Now that requires us to use the quotient rule. So y double prime equals negative 5 times, and then the quotient rule says low times the derivative of high, so the denominator times the derivative of the numerator, which is the derivative of x is 1, I'm going to write it in there. Minus, oh, it's low d high minus high, so we're subtracting the numerator times the derivative of the denominator, which is dy dx, or y single prime, all divided by the denominator squared, or low squared. So that's y squared. Interesting. Okay. So I'm supposed to be finding y double prime. This looks like y double prime. It says y double prime equals, but on the right-hand side of the equation, I have a dy dx. That's a little strange. If I were trying to find a rate of change, it wouldn't be the slope of a tangent line anymore. It would be the slope of the tangent line to the graph of the first derivative. Don't worry about that. But if I were given an xy ordered pair, I could plug those into x and y, but what am I supposed to do with that dy over dx? If only we knew what dy over dx equaled. Oh no, are you telling me that I have to plug that in place of dy dx? I sure am. It's just algebra. Painstaking, thoroughly enjoyable, not torturous at all algebra. All right, so I would say maybe let's make up a couple of common denominators and see what we can do about consolidating this a little bit. Doesn't hurt to stay up on our algebra skills. In the numerator, I'm going to write that as y squared over y, in order to have a common denominator of y. And then minus, there's a double negative there, so plus the x times the negative 5x, or it's really a negative x times negative 5x, makes 5x squared over y, and all of this is over y squared. We're almost there. Now I've got negative 5 times y squared plus 5x squared all over y squared. Well, I'm pretty sure that if we keep change flip, or if you want to think of this as y squared over 1 and then do a keep change flip, we're going to end up with negative 5 times, I can make this smaller now because it's going to be one fraction, y squared plus 5x squared over y to the third. So when we do keep change flip and we multiply by the reciprocal of this, we're going to be multiplying by 1 over y squared. So that y squared that ends up in the denominator is going to multiply in here with this y to the first power, giving us y to the third power in the denominator. And the other thing that we could do is we could distribute finally this multiplication by negative 5 into those two terms and end up with negative 5y squared minus 25x squared all over y to the third. Or perhaps the negative would be left in front of the fraction bar and only the 5 would be multiplied in, so that your two terms in the numerator remain positive, but the whole fraction is negated. Either way, this is a pretty nicely condensed version of a final answer to the question or the request for us to find y double prime. It takes a little practice to remember that you need to do that substitution for dy dx into the process for the second derivative, but you'll get used to it. You do a couple of them. And then the only other example that I want to work, we're at the 40-minute mark, so let's start trying to wrap this up. Let's do number 9. Let's take the derivative of an inverse trig function. And oh, this is nice because it just says y equals. Was the other one y equals? It was. Great. So dy dx, or y prime, equals, and then the derivative of the inverse sine function is 1 over the argument. It's actually 1 over the square root of 1 minus the argument 8x plus 1 squared, and then we have to use the chain rule and multiply by the derivative of the inner function, which is simply 8. That's the derivative of 8x plus 1. You could then go so far as to try to clean this up. Let's see, is that worth doing? 64x squared plus 16x plus 1. It's being subtracted from that one. I'm not so sure that that's going to be all that worthwhile. See if you can type this in as a final answer. I would certainly put this 8 up here into the numerator and just have it be 8 over the square root. I don't think I'd go any further than that. If you did, would you? Can you? She's such a baby. Let's multiply this out under the square root symbol and see what we get, just to make sure there isn't something unusual that happens as we try to consolidate this. So we've got 1 minus, and then when we square this, we get 64x squared plus 16x plus 1. And then we have to distribute this minus sign. So we're going to get 8 over the square root of negative 64x squared minus 16x, and then the positive 1 and the negative 1. Once we distribute this minus sign out here, it becomes a negative 1. Those are going to cancel each other out. And we've got this. There's a factor of 16 in there that we could take out. Let's just keep going to the moon with this thing. So we've got 8 in the numerator still. We've got the square root of 16 gets factored out, so I'm taking a 4 out, times the square root of negative 64 is 2 to the 6th, 16 is 2 to the 4th, 6 minus 4 is 2, so that's a 4, x squared minus x. And then the 8 and the 4 can reduce, giving us 2 over this square root. You could then rationalize the denominator if we wanted to go totally nuts with this, and write it as 2 times the square root of negative 4x squared minus x, all divided by negative 4x squared minus x. All right, I'm not taking it any further than that. Oh, look at her. She's so cute. It's painful. It is a little painful. Her nails are actually kind of digging into me so she doesn't slide off. All right, that is your tour through the wonderful world of wonderful world of implicit differentiation. I hope that ends up being helpful to you. Watch out for that hidden chain rule. It's all over the place when you're doing implicit differentiation. And when you're doing those second derivatives, don't forget to substitute back in for dy over dx. That is it for Chapter 3. Thanks so much. It's been a pleasure. See you in Chapter 4.